I wonder how many videos one teacher can make a day. We'll find out. Lots today. I'll go faster this time. All right, this one's all about Unit 2, Kinetics. All right, so a couple of things. We know that as a reaction occurs, you are going to have the reactants disappear. So we're using it up concentration-wise, and the products are going to appear. I can find the rate of disappearance by taking the slope of this tangent line, or I could find the rate of appearance by taking the slope of this tangent line. And we know that this is also related to equilibrium, that we could reach an equilibrium point. But right now, what I really care about is just how fast am I using up something and how fast am I making it. All right, so kinetics, we can write expressions. The rate of the forward reaction is equal to this rate constant K times the reactants to a certain power. But I could also do the same for the reverse reaction, and that's the connection to equilibrium. In kinetics, we only focused, just so you're aware, on one-way arrows, but it is, we know from our unit on equilibrium, it is possible to think about a reverse reaction happening, and we can write the same rate. Rate of reverse is a new K times the products, right, to a certain power. And so that's the connection to equilibrium, when the forward rate and the reverse rate are equal. So when these two things are equal, that is when we are at equilibrium, meaning the amount of reactants and products are not changing. And so what if I rearrange? I can say that K1 times the reactants equals K2 times the products, right? Set them equal if those two things are equal. And then what if I move the K's to the same side? Well, now I can call this a mega K, right? Instead of K1 over K2 for the rate constants, I can make this big K for equilibrium at products over reactants. So that's the connection between these two units. But let's go back to kinetics. There are two different ways that we can kind of solve for the rate law. The first is called the method of initial rates, or the differential rate law. Couple of things. You can have multiple reactants. So this is where we see a table and there are multiple trials. So in each trial or experiment, we change the concentration of the reactant. So maybe I double one reactant and leave the other constant. And then we measure the initial rate of the reaction. So right when it starts, what's the rate? The goal is to hold concentration of some reactants constant to see how changing the other impacts the rate of the reaction and helps us determine the order. And in the video, we saw how to do that. If you need a refresher, go back and study. But again, it's looking at how doubling something changes the rate. And so then the rate is equal to K times the concentration of your first reactant to a certain power times the concentration of the second reactant to a certain power. And you can continue with however many reactants. But the idea is multiple reactants. And then when we write the rate law, it will have the word rate. It will have this letter K. It will have an actual chemical there. And there, and really the only thing you're changing is M and M. Those will be numbers based off the order that you figured out. So the rate law looks like it has a lot of unknowns. The integrated rate law then focuses on one reactant over time. So time is involved with the integrated rate law. Time was not a factor here. It was just the initial rate. Here we're looking at time. It only is one reactant, or like our labs will have a pseudo first order where one essentially isn't changing enough to care about. So we assume it's first order, so we don't really worry about that. Or we assume it's part of the K, the rate constant. Anyways, mostly we're going to see one reactant. So one trial is done where the concentration of the reactant is recorded over a period of time, and we make three graphs: the concentration over time, the natural log of concentration versus time, and 1 over the concentration versus time. The most linear graph, which we look at R squared values closest to 1, will determine the order. You will not need to make a graph on your calculator for the AP exam. And then, based off the order, we can use the integrated rate law. And so this is for 0 order, this is for first, and this is for second. And so based off whatever graph is most linear, that will tell you what rate law to use. So let's say that we figure out a reaction is 0 order. Let's say a reactant is 0 order. What does that actually mean? And I think this is the direction AP is going to go this year. That means that if you double the concentration of that reactant, it will have no impact on the rate. So you add more of it, it does not make the reaction happen faster. You triple the molarity, no impact on the rate. You get the idea. The differential rate law would be rate equals K times that chemical to the 0. And here's the integrated rate law. So the concentration of that chemical at a certain time is equal to the negative rate constant times time plus the initial concentration. And the unit for K So when you solve for K in its zero order, will be the molarity divided by time. So pay attention to your time. Is it seconds or is it minutes? And then there's a half-life equation. The half-life for this depends on the initial concentration divided by 2 times the rate constant. So that's the amount of time it takes to cut in half what you started with. First order, what does it mean? It means if you double the concentration, the rate will double. If you triple the concentration, the rate will triple. So whatever you do to the concentration, the same thing happens to the rate. We have a differential rate law, we have an integrated rate law. So if they ever say to write the rate law, you can use either one. One is usually more helpful than the other. The unit for K, so when you solve for K in its first order, will just be time to the -1. So seconds to the -1 or minutes to the -1. And here's the half-life equation. Notice it only depends on K. It does not depend on the initial concentration. First order has a constant half-life. What that means is if I cut it in half and it takes 5 minutes, it's going to take 5 more minutes to cut that half in half, and then 5 more minutes to cut that half in half. And so that's one way you can identify first order. Second order, what does second order mean? If you double the concentration, the rate is going to 4 itself. If you triple the concentration, the rate is going to 9 itself, because you take that change in concentration and you square it. And then, so here's your differential rate law, here's your integrated rate law. -1 means 1 over, right? 1 over the concentration at a certain time. The units for K, if you solve for K, is the molarity to the -1, time to the -1, so pay attention to your time units. And then the half-life is 1 over K times the initial concentration. So typically what's going to happen is you are going to see 3 graphs, and depending on what is most linear will tell you the order. So in this case, all 3 graphs right here, we have the first order graph is the most linear, so that means this is a first order reaction with respect to A, and so we would use this integrated rate law, and a lot of times we're going to use this to solve for certain things, like what is the concentration after 20 minutes? Well, this is 20 seconds, right? So that's not that helpful, but what if I said 40 seconds? Right? Well, that's not on the graph, so I can't use the graph to figure it out. So I could plug in 40. I know my initial molarity from the molarity graph, so I can plug that in, take the natural log of it, and then we can solve for A. And we have our half-life equations, and then we have our differential rate laws. I just want to emphasize here that this and this are the same thing. It's just how you need to use them. They're both rate laws. One is more useful if you're looking for things referred to time. One, if you're looking for just the initial rate, this one is simpler and easier to use. Also, you can solve for K by plugging in a starting concentration, a concentration at a specific time, solve for K, or if you are able to, you can find the slope of the straightest line. That's another way to solve for K. So this is on the 2012 AP Chemistry FRQ. It was also on your mock exam number 2. So read through, pause the video, just skim through it to refresh your memory. Again, you watch the video, but here's what I wanted to point out most on this question. A lot of us struggle to remember to use the integrated rate law. So we have an experiment, and they tell me it's first order, which tells me this is the rate law to use. I have a mole sample and a volume, so I can find molarity, initial molarity here, so that's what I plug in. And then after 20 minutes, so we have a time, and I know the new concentration. So I know the concentration at a specific time, I know the initial concentration, and I know the time, and so then I can solve for K. Because it's first order, K units are time to the -1, so there is our answer. Now that I know K, what is the initial rate? So now I'm going to use the differential rate law. Rate equals K times the reactant to the power of 1. And so I know the initial concentration, that's this. I know the K from above, I can solve for the rate. And then you can read letter F, or hopefully you did your corrections. One thing to clarify from the video, energy diagrams versus Maxwell-Boltzmann. So this is an energy diagram or energy profile. We're graphing potential energy over the pathway. So reactants, transition state, products, endo, exothermic. You will see more of this in the thermo-chem mini lesson on Wednesday. But that is different than a Maxwell-Boltzmann. This is not a Maxwell-Boltzmann graph. These are all Maxwell-Boltzmanns. So, a couple of things. The graph can show one gas at 3 separate temperatures or 3 gases at 1 temp. So here's the idea. This particular graph that we're looking at is one gas at 3 temperatures, and the girls talked about in our video the ice cream. So when it's cold, when the gas is cold, we have a high peak here, and then I just drew in this dotted line represents activation energy. You can draw that at any point, whereas on the last graph, the energy graph, from here to the transition state, that was activation energy. Now this is activation energy. So totally different graphs. Anyways, I heat up the gas. You heat them up, you speed them up. So I heat up the graph, I increase the temperature, I increase the speed, I increase the chance of collisions, which means the area under the curve after the activation energy represents successful collisions. So if I have faster moving particles, there is more area under this curve representing more collisions that are successful. I can also do, so that's temperature again. Say I'm talking about area under the curve, so these ones collide, but they don't have enough energy. Sorry, I don't know. These collide, but they don't have enough energy. These collide, but because they're after the activation, they have enough energy to actually have a reaction. So temperature. Okay, what if I have 3 different gases? We can look at molar mass. So argon has a bigger molar mass, so it's moving very, very slow. Neon and then helium's tipping around. So all of this area here, the yellow and everything else, represents that helium is more likely to have successful collisions. Let's talk kinetics labs. So to start this unit, we put some hydrogen peroxide in a flask with some soap and food coloring, and we tried to make it go faster. We heated it up, it bubbled a little. We added a catalyst, and I shook the catalyst to increase the surface area. That helped a little bit, but then the best thing we learned was to increase the concentration. So instead of 3% hydrogen peroxide, I used 30% hydrogen peroxide, and we saw the elephant toothpaste demo. So this was just a practice lab. You guys had a bunch of Skittles, and you had 10% react each time, and you made some graphs. So again, you continue to do this for like 15 seconds, which means 15 passbacks. And so you made a big data table for concentration, which was number of Skittles, natural log of concentration, 1 over concentrations. You made graphs. You practiced instantaneous rate, which was just finding the slope of a tangent line. You figured out which graph was the most linear, and so then you figured out what the units for K were based off the order. You solved for K, so you used the integrated rate law to solve for K. So you plugged in your initial Skittles, you plugged in Skittles at a certain amount of time, and solved for K. And then you also took the slope of the straightest line, so you can compare the 2 Ks. Hopefully they were the same, and you calculated half-life. Okay, this lab was pretty straightforward, and it actually used the concepts from Beer's law. So you had crystal violet, which was bright purple, and it reacted with OH. So you actually reacted those just in a beaker, and you took a little bit in a cuvette, and it was still purple. So we have our rate law here, but one thing is we only focus on crystal violet. Here's why. The hydroxide concentration was over 1,000 times larger than the crystal violet. So basically we said, okay, if this is 1 mole and this is 1,000 moles, and we do minus x for stoichiometry, we're not really using up that much of this. So it's not really changing that much. So kind of like a differential rate law, right? If we hold something constant, we know it's not impacting the rate. So we called it a pseudo first order rate law because we ignored this because it was so much larger than this. So then what we did is we took this purple crystal violet reacting with the hydroxide, we put it in a cuvette, and we knew it was going to slowly get to a colorless product. So it's going to go from bright purple to a lighter purple until it was colorless. So we used a colorimeter like we did for Beer's law, and we tested after for every minute for 20 minutes or every 30 seconds for 20 minutes, the absorbance. And we used absorbance like concentration because Beer's law says absorbance is directly related to concentration. So if my concentration goes down, my absorbance will go down. So we use absorbance to replace concentration here, and then we created 3 graphs: absorbance versus time, ln of absorbance versus time, and 1 over absorbance versus time. You look for the straightest line to determine the order. You figured out the units for K once you knew the order. We took the slope of the straightest line for K, and then we calculated the concentration after 45 minutes using the correct rate law, and then we calculated half-life just for practice. All right, and then you also did the kinetic study of thiosulfate. So we had a catalyzed reaction here, and we used another first-order approximation. So the acid participates in the reaction to make it go faster, but we basically lumped it in with K, so we're ignoring the catalyst right now because it stayed constant the entire time. So it stayed constant. Well, the acid stayed constant the entire time. It was the thiosulfate that we are changing. So that's what we could pay most attention to. So you had 8 well plates. They were clear, and on a sheet of paper underneath, you numbered 1 through 8. And then you put the clear well plate on top. You added the acid and some water, and you put specific drops of the thiosulfate and into a grad cylinder, and then you mix them and recorded the amount of time. So what happens is when this reacts with the acid for this catalyzed reaction, it starts to turn this like yellowy milky color, and then you couldn't see the numbers anymore. So you recorded the amount of time it took for it to go from clear until you couldn't read the number anymore. And then you were able to graph the concentration, which we represented as the number of drops. So how many drops versus the time that it took to not see the number, the natural log of drops versus time, and 1 over the drops versus time. And we were able to find the order, write the rate law, and the integrated rate law. Super easy. This was a demo. I honestly can't remember if it worked, but it basically oscillates back and forth between 2 different colors to show you reaction mechanisms. It like works half the years and the other half it doesn't. So I can't remember. All right, the last thing is mechanisms. You guys did not really vote for this, and I'm shocked because we are not very good at mechanisms. So first thing, the only way you can determine a rate law is through experiments, like what we did in class where we created the graphs, or you have different trials for a different, like a differential rate law where you hold something constant, measure the initial rate, change the other thing, measure the initial rate. Mechanisms are proposed, but here's how you can check to see if they are valid. The sum of all the elementary steps have to add up to the overall balanced equation once you cancel out intermediates, and the mechanism must agree with the experimentally determined rate law. That means the differential or the integrated rate law that you got from lab. So how do they figure out the mechanism? They first experimentally determine the rate law, and then they come up with possible mechanisms and see experiment to eliminate least likely possibilities. But it can never be fully proved. You can't prove all of these steps, but you can kind of narrow it down what the possibilities are. So here's a great question. They experimentally determine the rate law is rate equals K times NO times Cl2. And so first, is NoCl2 a catalyst or intermediate? So here are all the steps. Here's the balanced equation. Well, I see that I make NoCl2 in step 1 and then use it up, so that means it's an intermediate. And then which step occurs the fastest? So here are my 2 steps. So we know that if you draw a line under the rate determining step, the slow step, box everything up into the left, use the stoichiometry, that gives you the rate law. You can't use the stoichiometry from a balanced equation, but you can from the steps of the mechanism. So if I drew a line under this one, and box everything up into the left, no intermediates, I would have NO squared, because there's NO and NO, and then Cl2, which is not the rate law. So that means the first one, let's erase that, that first step has to be the rate determining step, so that is our slow step. And then which step determines the overall rate? The slow step, that first step determines the overall rate, and it matches the experimental rate law. Hopefully that was helpful.